All right, so with this recursive algorithm, we get kind of a magical thing happening with the string edit distance, a bit like what happened with the towers of Hanoi. So I didn't really know what the optimal sequence was, but I was able to figure it out by defining something recursive where I only had to think about, well, what's the very last thing I have to do? Am I going to chop something off of the first string? Am I going to chop something off the second string? Or am I going to try to either swap or mash the last element of both? And it's not clear which one I need to do, but the recursion will sort it out. Okay, so that's very nice. The one catch, though, is this. While this may work and will give you the correct answer for the optimal number of steps, this is not what you want to do in practice. It's very inefficient. You can see this because it actually does 3 recursive calls for every recursive call. So this is worse than Fibonacci even. And actually, it's even worse than that because when I do a recursive call in the first two, I'm only able to cut one of the inputs down. So this is a 2-parameter function, and so you could see, I mean, Fibonacci was already exponential. It was branching out. This is going to branch out even more, so it's at least exponential. That's not going to scale well enough for us to use it on large strings. So we need something that's a little better. And here's where memoization comes in. Okay, we're going to use the same trick that we used with Fibonacci to make a more efficient version of this. So let me show you what we're going to do. We have to remember the matching of all possible substrings from the first string to the second string. Okay? So if we include the empty string, then there are 1 plus the length of S1, so that's the empty string plus all possible substrings of S1, times 1 plus length of S2, so that's the empty string plus all possible substrings of S2. That's the number of different matchings we can do. So, matchings from a substring of S1 to a substring of S2. So in particular, if we assume that the length of S1 is approximately equal to the length of S2, then this is saying we need to store O of n squared numbers, okay, or costs. Okay, so that's interesting. Oh yeah, sorry, I meant to say if len of S1 is approximately equal to len of S2, which is equal to n, then we need to store big O of n squared costs. Okay, so that's how many possible substrings we need to consider matching, and that's the most we're going to need to store in memory. So this is definitely, again, a space-time trade-off. We're going to take O of n squared space now. I know we normally talk about time, but we're talking about storage here. And we're going to store that number of things. And hopefully that's going to save us from having to redo certain substrings that we already know how to match. So the best way to do this actually is to organize not in a dictionary, but in a table. Okay, so let me show you what a table looks like for Chris versus Chase, for example. So here's what we've got. Okay, let me show these side by side here. Okay, so what I'm going to do is I'm going to put the first string, all the characters of the first string along the row, including the empty string. So I'm going to have one character here which represents the empty string. And then I'm going to put the second string along the columns. So what a particular element in this table represents is the optimal cost to match a substring from the first one to a substring to the second one. So what you can see is the base case occurs in the first row and the first column. So matching the empty string to the empty string costs nothing. Matching the empty string to C costs 1. Matching the empty string to CH costs 2. So see what this means is match the empty string to the substring up to ch. Okay, match the empty string up to the substring including a. That costs 3, 4, 5. And it's the same thing down the row. Now I'm going to match, C to the empty string up here. That costs 1. Now I'm going to match ch to the empty string up here. That costs 2. I'm going to match chr to the empty string. That costs 3. So the first column in the first row can be filled in like that. Now, just to give you another example, this element here represents the optimal cost of matching chri to chas. And we find that that's 2. Okay. This element here represents the optimal cost of matching chri to chase. All right. So I think filling in the first row and the first column isn't too bad because those are just the base cases. You see, every time you add another character to a substring, you increase the cost of 1. So you just do a range up here and then a range down here. But how do we fill in the rest? So let's look and see, well, which one of these depend on the others. So let me add some arrows here to show which ones depend on the others. And I can relate it to the recurrence up here, to the recursive definition. So if I'm at the end, that relies on chopping the last character off of the first one. So that is here. That's additive S1 from 0 to the second last character. But matching to the entire string S2. Okay, so that's this entry up here. This one, the second one here, this is saying chop the last character off of the second string, but match to the full first string. That's this down here. Okay, and now this last one is saying chop both of them off, and that's this diagonal. Okay. So we can write some code to do this, because actually what we notice is if we fill in the first row and the first column of this table, we can then fill in each row one by one. So if I know, and actually let me do it by hand here. So if I know that the first row is 0, 1, 2, 3, 4, 5, and the first column is 0, 1, 2, 3, 4, 5, the first element I have to fill in is row 2, column 2. So it ends up being 0, but how do we get that? So, well, we look up to see how much did it cost if we were going to delete this character and then match to this one. That cost 1. Okay, and then we know that we have to add this character back. So that would have cost 2. That's definitely, okay, that's that. Similar thing, this would have cost 2 to come over from this direction. But actually, if we match them, it costs nothing. So the possibilities we have are 2 coming from up top, 2 coming from over here, or a cost of nothing. Okay, let's jump to the end and just look at, so you can keep filling these in. You can see that as I loop through, all the dependencies are satisfied. So if I filled in the first row and the first column and I start looping here, I go here, well, I've got everything I need. I filled this in. Okay, now I go here. I've got everything I need. I just filled that in. I already had that. I already had that. Fill this in. Okay, now I go here. I've got everything I need. I just filled that in, and I've got that, and I've got that. So fill that in the same way, fill it in the same way. Now I go to the next row. Well, same thing. I already filled that in, so I can look at that. I'm over here. Well, I filled in the row before this, so I've already filled that in. I just filled that in, and I filled that in. So that's how you're able to go in this so-called raster order, where you go left, right, row to row. So that's how you fill it in. But yeah, and let's just look at the very last one. So once you fill all these in, you get to the very last element here, and you have to fill that in. So here we go up and we say, okay, what if I tried to match Chase to CHRI? that costs 3. I've got to put the s back, so that costs 3 plus 1, that costs 4. Okay, what if instead I match CHAS to CHRIS? Well, that costs 2, and I've got to put the E back, so that costs 2 plus 1, that costs 3. Okay, so that's actually an optimal here, we see. So 3 is better than 4. If I try to come from up here, I would have gotten a cost of 4. That's not as good as if I came from over here. Now, what if the other possibility is, what if I try to match CHRI to CHAS? In that case, it turned out to be a cost of 2, but then I'm forced to swap in the E for the S or the S for the E. That costs 1, so 2 plus 1 is 3. So actually, coming from the diagonal or coming from the left, in this particular example, gives you the same result. So what that's saying is you can either choose to chop off the S off the end of CHRI, or you can choose to add the E, or you can choose to swap in the E for the S. Okay. So let me start to write some code to do this. I'm going to keep this table up here, and I'm going to start to write some code. Oh, actually, let me also show you just real quick one more example. So we also had the school and fools, and I told you the answer was 4. Let's check to make sure that's true. Oh no, actually the answer was 3 because I didn't spell it right. Okay, hang on. School to fools. Okay, yeah, there we go. There the answer's 4. All right, so I just want to show you that. But let's keep this up here and see. I'll start to fill in code and you can finish it. This is now an O(n) squared algorithm. This is a lot better because I just have to loop through a table. Well, tables are n squared. I have the loop through the rows, and then for each row, loop through the column. So let's do it. So I would say def, I'll start writing the code and you'll finish it. So def edit s1, s2. So I'll say m is the length of the first string. And then n is the length of the second string. So let me make my table. So I'll say table is equal to mp.zeros, m plus 1 rows, and n plus 1 columns. Right? Because I need to, for the empty string, I have one more row than I have characters in the first string, and I have one more column than I have characters in the second string. Okay. I'm going to need NumPy here. This is a quick way to make a two-dimensional array using NumPy. Okay. This actually takes a tuple as an argument. Okay, whatever. So the first thing I could do is fill in the base cases. And the neat thing is, okay, I'm not going to need to do this with recursion. I used recursion to design the algorithm, but actually, once I do memoization, I see that there's an order that I can fill in the entire table with loops instead of recursion. So this is now an iterative algorithm. So the base case is what I can say is the first row of the table, I'll just do this for you, but this is saying the first row of the table, I'm going to take out a slice, which is the first row and all the elements in that row. That's going to be equal to mp.arange n plus 1. Table, colon, so the first column now, so column index 0, all the elements in that, that's going to be equal to mp.arange n plus 1. Okay, so let me first, I'm just going to print the table and I'll show you what this looks like. So if I say edit of school and fools, let's just make sure I'm setting this up right. Okay, so it looks like I got the first row and the first column set up properly. Okay, so now what I need to do is loop through all the rest of the rows. So I'll say for I in range 1 to n plus 1. Okay, so that's going to loop through the rest of the rows. And for each row, I need to loop through, so for j in range 1 to n plus 1, I need to loop through all the columns. And so now what you need to do is these 3 cases. So look, so check, the table at I minus 1, so that's the one above, I minus 1, 0, plus 1, right? check table at I j minus 1 plus 1. And then check table at I minus 1 j minus 1 plus 1 if the string at index I minus 1. So we'll say we have to add 1 to this case if the string at index I minus 1 is equal to first string at index I minus 1 is equal to the second string at index j minus 1. So that's what you got to fill in. So store table I, j as the min of the above possibilities. And the result is going to be the table in the lower right hand. So it's going to be the last row and the last column. So that's it. So fill this in and you'll be done. On Monday, what we're going to do is look and see in class, we're going to write an algorithm that will work on top of this, which actually will show what is an optimal path that you can take. So you really can think about this as taking a path from the lower right to the upper left, following these arrows. And just to show you, there are certain arrows which, if you follow them, you'll actually get. So now I'm only drawing the arrows that are optimal. So there are a couple ties, like moving from here to here. I tie if I look at the upper diagonal or if I look at the left. But there are a few ways of starting at the end and getting back to the beginning. And that tells you actually what was the sequence that realized this cost. And there are a couple sequences that tie, and so you're going to enumerate those sequences in class on Monday. But for now, just finish this code and you'll be done the module. All right, thank you. This is kind of a heavy module, so thank you for sticking with me on this. I think we're going to have a good week.